All right, let's take a look at a couple of new parent functions. First one is going to be the sine function, treating sine a little bit differently than just a ratio now. The basic notation is f of x equals sine of x. For our arrow, it's just going to be sine of, and the key points on the sine function are going to be what we call the quadrantal angles on the unit circle. So I'm going to draw a little unit circle here. And what we're going to focus on is these places where the x and y axis intersect the unit circle at 1, 0, at 0, 1, at -1, 0, and at 0, -1. And we're going to for the sine function, since you remember these are cosine x, sine x pairs. So the sine, we're going to be focusing on the y coordinates and the angles that get us there. So we're definitely still changing an angle into a y coordinate here. And so the angles as we move around are 0 radians. Pi over 2 radians is up at the top of the circle. And then pi radians is over here. 3 pi over 2 radians is down here, and then we complete a circle with 2 pi radians. And if we follow along with the y coordinates, we see that that one is 0, and then 1, back down to 0, down to -1, and back to 0 again. Okay. And so if we plot these points, what we're going to do out here, we'll just pick a point out here and say this is 2 pi. And so halfway between those would be pi, and halfway between those, this one would be the pi over 2, this would be the 3 pi over 2. 0, 1, and -1 are the points that we're looking at, so we'll put a point here at 1, and one at -1, and we have a point at 0, 0, pi over 2, 1, pi, 0, 3 pi over 2, -1, and 2 pi, 0, and the shape of the graph is kind of this S-curve that goes along here like that. We need to get accustomed to seeing that as the basic shape of a sine curve. Okay? Now, because we could continue going around the circle and we have all of these other angles that just continue cycling those same numbers, the coterminal angles with all of these. We could also have gone backward around the circle and gotten points at -1 and then at 0, back at +1, back at 0. And so I'm going to put this one in there not because it's part of the main thing, but to emphasize that what we have here is this wavy curve that will go on forever like that. We don't talk about the end behavior of this because it doesn't go to infinity or negative infinity, and it doesn't settle in on a particular number. Okay, so it's difficult to describe what that end behavior is. Okay. This does have a domain of all real numbers. We can put any number in there, but the range now we'll do in interval notation is just from -1 to 1. It never climbs above +1, never dips below -1 on the outputs. We have learned something about coming back from this direction. We know that that is the inverse sine. But the inverse sine on the calculator only gives us half the story. Okay. We also have, from here, if we did the inverse sine for a particular angle, it might give us this angle right here, but this point has the same y coordinate over there. And so pi minus that is also a potential solution. So we'll put that in as pi minus the inverse sine. And then, of course, we have all the coterminal angles, so we can add a plus 2 pi in to both of these. So it gives lots of potential solutions to this. All right, some of the features of this graph. The length here, how far it takes or how wide the basic S-curve shape is, okay, is called the period of the graph. Okay. The natural period is 2 pi, because that's how far it is around the circle in angles. So in radians, 2 pi radians around there, and then it starts going again, and that's what creates this repeated nature of what's going on. We can also see the period, we can see it graphically here, but we also see it here as the difference between this first and last point on here. So I'm just going to flip that sideways and point out that in the table you can see the period there. There is a height to the graph. Okay? Actually, before we do that, there's also a center line. The center line is referred to as the axis of oscillation. It has a natural equation of y equals 0, y being an output. Here's the output, and there's a 0. So we can read the axis of oscillation off of any of these output points. Okay. The height of this, okay, that's an output thing. That is referred to from the axis of oscillation to either the high point or the low point. That distance is called the amplitude. Okay. We can see the amplitude as this gap right here. Okay. And then this point starts here. This is the starting point that hasn't been shifted to the left or the right. This is called the phase shift. Okay. The phase shift naturally is x equals 0. That's an input of 0. Well, here is where our natural input is 0, and so we'll always be able to read the phase shift off of that. Okay. All right. That is what the parent sine function is all about. It's a lot of vocabulary and information there. We are also going to do a parent cosine function. I'm going to pause the video here for a moment. All right, so the cosine parent function, cosine x, the arrow starts the same. We're still changing angles into now, though, x-coordinates, right? Because the cosine function is the x-coordinate of those points on the unit circle. So still the key angles of 0, pi over 2, pi, 3 pi over 2, and 2 pi. But now our x-coordinates are 1, then 0, and then -1, and then back to 0, and back out to 1. So this one kind of starts at a big number, goes middle, small, middle, big. I think about it that way often. If I'm marking these points then, so here's my 2 pi and my pi, and there's my pi over 2 and my 3 pi over 2. I'll go ahead and throw the -2 pi in here, negative pi over 2, and -3 pi over 2. And we have a point at 0, 1. And then pi over 2, 0, pi, -1, 3 pi over 2, 0, and 2 pi, 1. And so this has a similar looking shape to the sine function, except that the sine function starts in the middle and goes up. The cosine function starts at a high point and drops down. Okay? So that's important to remember when you're deciding which function it is that you're actually looking at. We can fill in this part. If we had gone backwards around the circle, it would look like that. So very similar looking things, and it actually is just a shift of one over the other. Okay, but we're still going to read period and those kinds of. It still has a period of 2 pi, still has a natural amplitude of 1, still has a natural phase shift at 0, and the axis of oscillation still here at y equals 0, which we can still pick off of any of these y coordinates that are 0. We can still see the period here. Okay. The domain is still all real numbers, and the range is still the numbers from -1 to 1. We can still read the phase shift off of this part. And this gap between those still tells us about the amplitude. Obviously, when we've done transformations to these, some of those numbers may change, and that's why we're pointing out where you can spot them there. The inverse operation to this is the cosine inverse, but we know that's only half the story. The other part that we will need is the negative of the cosine inverse. Okay. You can explore that a little bit and see that that's the case, plus our 2 pi n for those coterminal angles that have the same values of cosine. All right, so again, the point, sometimes it's easier to see the period on a cosine function because it's high point to high point or low point to low point, but not difficult really in either way. All right, those are the sine and cosine parent functions.